Hello and welcome to this SMARTEC webinar. Today's presentation will have a duration of about 20 minutes. By now you should hear my voice through your PC speaker or headset. If you have any questions during the presentation, you can use the question panel on the right side of your screen. Write down your question, and at the end of the presentation I will answer those questions or I will follow up by email if you prefer. Later this week you will be able to receive this presentation in PowerPoint and additional information as well. Today's presentation is entitled ATTS, Automated Test System for High Reliability Pipeline Leak Detection. The content of the presentation will be as follows. First, I will start with an introduction on leakage detection through distributed temperature sensing, in particular for pipeline leak detection. I will show some application example, and then we will discuss how those systems can be configured for optimal reliability and how to test that reliability. And I will conclude with recommendations and conclusions. Let's start with a little introduction on leak detection. Pipeline leak detection is based on monitoring the temperature profile along the pipe itself. And leak detection is performed through temperature anomaly detection and analysis. So leak detection is also localized through the time of flight, and therefore it allows mapping and exact localization of the leak itself. It is also possible to connect the location of a leak with a geographic information system so that the exact location can be displayed on a map. In general, when we have a leak from a pipeline, we get two main effects, either a local warming in the surrounding of the pipeline or a local cooling, again, close to the pipeline itself. This can be due to different phenomena. First of all, in the case of pipelines such as ammonia or liquefied natural gas, we observe a cooling due to the liquid evaporation. So the liquid being carried in the pipeline evaporates and creates a local cool down. Cooling is also observed in the case of pressurized gas pipeline because the gas expansion from the inside pressure to the outside pressure of the leak causes a temperature decrease of the gas and therefore cools down the pipe and its environment. We can also have hot spots or temperature increase when we observe leakages of crude oil or other liquid that are warmer than the soil around the pipeline. And also in some cases we can observe a change of thermal capacity due to liquid release. For example, a wet soil will change its temperature more slowly than a dry soil due to daily temperature cycles. Those systems based on distributed fiber optic sensor offer high sensitivity for the detection of very small leakages, and they can also localize the position of the leak with a 1 meter accuracy. The measurement systems are based on a combination of a readout unit and a measurement cable. The measurement cable is installed along the pipeline and can detect and localize hot spots or cold spots along the pipe itself. For example, here, if we have a temperature increase at a specific location due to, for example, an oil leak, we will observe this temperature increase and localize it. And if we have a temperature drop at another location due, for example, to a gas pipeline leak, we will see that cold spot and also obtain its position. The components that are used to implement such a system are the cable itself, which is a simply passive optical fiber cable installed along the pipeline. It is designed for being used in outside environment and buried. It's insensitive to electromagnetic fields, corrosion, etc., and is fast and quick to install. And the readout units that cover different distances allow an automated and remote operation and can send alerts via Ethernet, SCADA, and so on. Finally, a data management software allows real-time data management and interpretation and automatically identifies leak locations by observing the temperature changes, for example, and then it can display it on a map. As in this case, you can see a leak has been localized and shown on a 3D plot of this ammonia plant. The main advantage of such a fiber optic sensor for pipeline monitoring are first of all linked to the nature of the optical fibers, so they are immune to electromagnetic interference. They are intrinsically safe, so they can be used in explosive environments. They are passive, so the cables don't need any electrical power and can monitor very long distances. The cables are small and lightweight, and the fiber is at the same time the sensor and the data transmission link. Those systems offer high sensitivity to detect small leaks and very long measurement range, so they can be a very cost-effective solution for pipeline leak monitoring. Here's a couple of application examples of this technology. We have installed a system of this type in different ammonia pipes, in particular within ammonia plants for the Yara in Italy and France, and for Pecrin and Borealis in France. And other type of pipelines include copper concentrate pipeline in Chile, seawater pipeline in Qatar, oil pipeline in Italy, and brine pipeline in Germany. Here's a couple of pictures from real installations on above ground pipelines. For example, in this case, an ammonia pipe. The cable in that plant was attached below the pipe, so that if the ammonia escapes, it will cool down the cable and allow detection. Here are some other examples of ammonia pipelines in plants. So you can see they can be above ground or close to the ground. And so typically the cable covers the whole length of the ammonia pipe in a given plant. And finally, here's an example on a smaller pipe in a vertical section and an horizontal section. Now I'd like to present a quick result from a simulation. In this case, about 1 kilogram of ammonia, liquid ammonia, was poured on a pipeline equipped with the optical fiber cable. You can see the pipe with the black colors that hold the cable in place. And as expected, when this simulated leak occurred, a quick temperature drop was observed. Here you can see two tests that were performed a few minutes from each other, and you can very clearly see a temperature drop from about 10 degrees to -5 in the first case, and from 10 degrees to about 4 degrees in the second case. The two tests were different in terms of the quantity of ammonia and the speed at which the ammonia was poured on the pipe. Now here you can see the temperature change as a function of the position along the pipe with regard to the previous measurement. So you see that in normal condition it stays within those boundaries, and now you see the leak occurring. So in this case, at a very specific location, 350 meters from the cable begin, we have observed a rapid temperature drop from one measurement to the next, and this is really the indication of an ammonia leak that the software can detect automatically. So now that we've seen that it's possible to detect ammonia leaks or other leaks with this system, the next question that we received from our customer is how we can make this system part of a security safety barrier. So in this case, there is high demand on the availability of the system, and typically in the chemical industry, this is measured with the SEL level 1 or 2. And these levels really indicate the probability of failure on demand. So if there is a real leak, what is the probability that we will really detect it, so that the system will be up and running and will perform the measurement and will correctly identify the leak. So the higher the SEL level, the higher the required probability of detection is, and therefore the higher demand on availability of the system will be. The first way to address these needs is by increasing redundancy. So if you have two systems that measure simultaneously, even if one is down, there is still a high probability that the second one will be measuring, and therefore the global availability and reliability of the system will improve. So in this case, for example, using two instruments connected to two separate cable loops, if we have a broken cable at one location, we will be able to measure clockwise from the instrument to the breakpoint and counterclockwise in the other end of the cable. And also if the other cable is broken somewhere, we can still measure the whole length of pipeline. And finally, even if one of the two instruments is unavailable under maintenance, etc., there's still full operational sensing capability along the whole pipeline. However, often it is required to prove that this availability is really realized in an application. There are ways to prove the SEL level by a theoretical calculation, what we call a paper evaluation based on mean time between failure. However, since those alarms are really infrequent on a typical ammonia plant or oil pipeline, there might be years and years before any real leak is detected. It's quite difficult for operator and regulation bodies to trust just this paper evaluation and be confident that in one day, in 10 years, when the real leak occurs, the system will really set off an alarm. So the operators and regulation bodies prefer an active approach where the system is regularly tested in service. Up to today, the usual approach has been to conduct periodic leakage simulation. For example, once a year, someone would go to a location and simulate a leak by diversing ammonia or cooling down the cable with a CO2 extinguisher and verify that the system really responds. So these tests are of course very useful, but they are quite costly and therefore infrequent. So if the failure of something occurs just a few days after the test, 1 year might go by before this problem is really detected. That's why we have developed what we call the ATTS device or automated trip testing system. It's a device that offers the possibility of automating this procedure and therefore implement it on a much higher frequency. Therefore, the ATTS can also be used to quickly detect any malfunction in the system. How does the ATTS work? The ATTS is a device that is fully independent from the DTS measurement system and is located between the DTS and the pipeline under monitoring. And what the ATTS does, it cools down or heats up a short section of fiber at the beginning and at the end of the loop in a way that simulates the temperature drop or temperature increase that is expected in the case of a real leak. This can be done very frequently, for example, every hour. And what we expect is then to see an alert triggered by the DTS at this location every hour when this test is performed. The ATTS can also record the reaction time and therefore can statistically evaluate the availability of the system. So it can tell you that over 1 year, for example, 10,000 tests have been done and 9,993 have been successful. And the average reaction time was so many seconds, etc. Another advantage is that since the ATTS is placed both at the beginning and at the end of the cable, it's possible to make sure that the whole line is available. So if the cable is broken somewhere, we will see the temperature drop at the beginning, but not the one at the end of the cable, and therefore we can also identify those failures. These failures are also identified by the DTS, but this doubles the possibility of early detection of such an event. Here is how the system is configured. The cooling or heating device is simply a Peltier cell with about 1 meter of fiber coiled on it. This is controlled by the ATTS controller, and the ATTS controller transmits a trigger signal to the plant controller. So the chemical plant controller knows when test is underway, and at the same time it receives the alert from the relay module. So one of the relay will be configured to trigger if the leak is detected in the test zone where the ATTS is placed, and a different set of relays will be used for zones of the real pipeline. So when the ATTS triggers a cooling event, it will not trigger a pipeline alert, and therefore the pipeline will not be shut down, for example. But at the same time, the plant controller can verify that after receiving the trigger signal, within a few seconds, it will also receive the corresponding alarm from the relay module. At the same time, the ATTS contains a statistical database so that those data are also stored in the ATTS itself. Here's a picture of the ATTS. So it's a rack-mountable unit that can be installed together with the DTS, multiplexer, and relay module, and contains all the electronics and optical and the cooling device that are necessary to automatically implement this concept. And here you can see an example of usage of ATTS. So we're measuring the temperature at the ATTS coil location. As you can see, the temperature is normally about 23 degrees, and once an hour you see this sharp vertical drop of temperature from 23 to -5, and this is an indication that the cooling has occurred and was correctly identified by the measurement system. Of course, it's also possible to combine the active approach of the ATTS and the redundancy approach to increase even further the availability and the reliability of the system. So in this case, we have two fully redundant systems, each one with its cable, ATTS device, and ATTS device. And these two systems can then be combined by a SEL-rated voting system, for example 1 out of 2, so that will increase even further the reliability. In this slide you can see a picture of a real installation for an ammonia plant. You see the fully redundant system, so in the top part you see ATTS, multiplexer, relay module, distributed temperature sensing system, and server, and the same is replicated in the lower part. And so the two systems work fully independently from each other, and then they are combined at the plant level through the plant controller. So in summary, the functions of the ATTS are to enable frequent tests of the wall measurement and alarm chain. That enables the verification of the correct functioning of the system every hour, even when there are no real alarms triggered for many years. Therefore, this drastically reduces the detection time of system malfunction, and they can also provide a statistical evaluation of the system availability to justify a given SEL rating to the regulation authorities. This is what is called the proven by experience approach. In general, when an SEL level is required, a single system with a TTS is a suitable configuration, and when SEL2 level is required, then we need a redundant system with a redundant ATTS and the voting system. So this brings me to the conclusion of this presentation and some recommendation. Distributed fiber optic sensing are ideal transducer to detect and localize small leakages of ammonia, oil, gas, and other harmful substances. And in some cases, high availability and reliability are required for a given application. SEL 1 or 2 can be achieved by a combination of an automated trip testing device and statistical analysis using the proven by experience, by implementing a proper redundancy, and by regular maintenance and online testing of the system. And this brings me to the end of my presentation. And if you have any question, again, you can use the question panel on the right-hand side, and I'll be happy to answer those questions now. Thank you very much.